Hi everyone, I am Madam Rosmaya. Welcome to my channel. In this video, we are going to discuss on molar heat capacity and degree of freedom. So first, what is ratio of gamma? Okay, ratio gamma represent ratio of principal molar heat capacities, which is equals to molar heat capacities with constant pressure and constant mass divided by molar heat capacity with constant volume and constant mass. So we are going to prove this equation. Okay, and CPM. We are going to prove that CPM, molar heat capacity with constant pressure and constant mass, and molar heat of capacitor with constant volume and mass, depend on the degrees of freedom. Okay, first step. For 1 mole of ideal gas, the internal energy is given by half FRT. Okay, in the previous lesson we've discussed and we have proved this equation of the internal energy, which is equals to half NFRT. So the N for 1 mole is 1, so therefore we get half FRT. From the first law of thermodynamics, delta Q equals to delta U plus work. So from the previous lesson also, we have discussed the equation for the heat equals to CVM delta T. So the N is 1. So we get delta Q equals to CVM delta T. So we are going to substitute here. And then from the work done for constant volume, here is constant volume. So therefore, there is no changes in the volume. So it is 0. So when 0 times the pressure, so we get 0. So that's mean work also 0. So now if work 0, the equations become CVM delta T equals to internal energy delta U. So we rearrange the equations become CVM equals to delta U per delta T. So this means change in internal energy divided by change in temperature. So as the change in temperature approaches 0, so we can write as CVM equals to du by dt. So this means we differentiate the u here equals to half FRT. F and R is a constant. So we derive this with respect to T. So we get half FR. So we use derivation rule. Okay, we use derivation rule for this equation. So we get half FR. So we have proven that the molar heat capacity with constant volume and constant mass is directly proportional to the degree of freedom. So it depends on the degree of freedom. Okay, we can do the relationship between CPM and CVM. Okay, where in the previous lesson we have derived this CPM minus CVM equals to R. So we substitute into the equation above. So we get CPM equals to R plus CVM, and we substitute CVM into the equation here. So we get CPM equals to R plus half FR, and we simplify this, so we get half F plus 2 times R. R is molar gas constant. Okay, so this two, another one CPM and both CVM and CPM, it is shown that CPM and CVM depends on degree of freedom. Okay, we continue from these two equations. Okay, gamma is equals to CPM per CVM, so we substitute these two into the equation here. Okay, CPM is half F plus 2R. Okay, and CVM is half FR. So we can cancel out half, and also we can cancel out R. So the gamma equals to F plus 2 per F. Okay, ratio of the molar heat capacity. So we get F plus 2 per F. So for monoatomic, in the previous lesson, also we discussed that the degree of freedom is equals to 3. So we substitute into here 3 plus 2 per 3. So gamma equals to 1.67. Okay? So for monoatomic, the ratio of molar heat capacity is 1.67. For diatomic, we do the same. We substitute degree of freedom equals to 5. So we get gamma equals to 5 plus 2 per 5. We get 1.4. And lastly, for polyatomic, F equals to 6. Gamma equals to 6 plus 2 per 6. So we get 1.33. So this is the special characteristic for each type of atom. For monoatomic, gamma will be 1.67. For diatomic, gamma will be 1.4. And for polyatomic, gamma will be 1.33. Okay, so the table below is the conclusion from the calculation in the previous slide. So the table below shows the calculations to obtain gamma for different types of gas. Okay, so this is also what we have discussed before. So CPM minus CVM equals to R, gamma equals to CPM per CVM, and gamma equals to F plus 2 per F. So we, for the given CVM and CPM and molar heat capacity for certain gas, example given here helium, okay, we calculate the gamma, we get 1.67, and for argon also, we get 1.67. Okay, so we can conclude that for all monoatomic, the gamma is 1.67. Okay, same for diatomic. For the CVM and CPM, and the relationship between CPM and CVM here, and we calculate the gamma 1.40 for oxygen, for hydrogen 1.41. So it's about the same. And lastly, polyatomic, we do the same for carbon dioxide and hydrogen sulfate. So we get 1.30 and 1.33. Okay, so this is all the formulas that we have derived from the previous lesson and for today's lesson. Okay, we try one example. Find the number of degree of freedom of molecules in a gas whose molar heat capacity at constant pressure, CPM, equals to 20 joule per mole per Kelvin. So the solution is, so we are going to determine the F degree of freedom, and given that CPM equals to 20 joule per mole per Kelvin. And from the equation we have derived before, CPM is equals to half F plus 2 times R. So we substitute the CPM given 20 equals to half F plus 2, the R is 8.31. So we get F equals to 20 times 2 per 8.31 minus 2. And the answer is 2.81. But F is a number of degree of freedom, so we cannot write in the decimal number. So we must convert it to the integer form. So the 2.81 is a decimal number. So you must write in the round it off to 3. Okay, the nearest significant figure is 3. The nearest integer is 3. So the number of degree of freedom of molecules in a gas whose molar heat capacity at constant pressure, CPM equals to 20 joule per mole per Kelvin is 3. Okay, we try the second example. 819 joule of heat is added to 2.14 moles of an ideal gas so that its temperature increases from 11.5 degrees Celsius to 30.0 degrees Celsius at constant pressure. So the gas does 216 joule at work during the expansion. Calculate the change in the internal energy of the gas and the value of gamma. Okay, given that the heat is 819 joule, the heat energy, number of moles, 2.14, and the change in temperature is 30.0 minus 11.5, we get Okay, didn't write here, but we don't have to convert to Kelvin, because if we convert to Kelvin also we will get the same answer. Okay, to convert to Kelvin we just add plus 273 for both. So if we minus, the 273 is cancelled. Okay? So it doesn't matter if you if you write the change in temperature using a unit degree of freedom, degree of Celsius, sorry. So the work done is equals to 216 joule. Okay, given here. Okay, now we can do the question A, the change in internal energy of the gas. So we use first law of thermodynamic, state that delta Q equals to delta Q plus work. Okay, so delta U is delta Q minus W. Okay, we bring work to the right side, become minus. And substitute the 819 joule, okay, for the change in heat energy. So minus to the work done, 216. So we get 603 joule. So this is the internal energy of the gas. Okay, next, to determine the value of gamma, okay, ratio of molar heat capacity. So this is given in the question. Okay, so we can use CPM per CVM. Okay, this is the definition for gamma, molar ratio of molar heat capacity, CPM per CVM. Okay, to get CVM, we use the relationship between CPM and CVM. So CPM minus CVM equals to R. So CPM, we bring R to the right side, become CPM minus R. This is equals to CVM. So we can substitute here. So we get CPM per CPM minus R. Okay, now for CPM, okay, we can use this equation. Delta Q equals to N CPM delta T. Because the question, we go back to the question. So the question mentioned that this data, okay, the information here all is at constant pressure. Okay, at constant pressure. So the heat calculated must use CPM. So we use CPM. So that's why delta Q equals to N CPM delta T. Okay, so now we can calculate CPM. We rearrange the equation here, become CPM equals to delta Q per N delta T. So delta Q is 819 joule, number of moles is 2.14, and the change in temperature is 30.0 minus 11.5. Okay, this is in Kelvin, and the answer is 20.7 joule per mole per Kelvin. Okay. So as I mentioned just now, I repeat again, the temperature here, even though we didn't convert it to degrees Celsius, so it is understood that the 273, when we minus, it is cancelled out. Okay? So that's why here the unit is joule per mole per Kelvin. Okay, for temperature here, Kelvin. Okay, so now we can calculate the gamma. Okay, CPM is 20.7 divided by 20.7. Again, here CPM minus R is 8.31. So the answer for gamma is 1.67. So what does this mean for 1.67? So for 1.67, this means that the gas involved here is the monoatomic gas. Okay, refer to the table that we have in the previous slide. 1.67 is the monoatomic gas. Okay, so this is exercise for you all to do. So do this exercise, and we will discuss this exercise in the next lesson. Okay, that's all for today's lesson, and don't forget to subscribe to my channel if you like the video, and thank you for watching.